Hello, welcome back. I'm going to continue my discussion on RSA fixed points. Today, I'm going to show to you how to compute the number of fixed points for a given RSA function. Okay, so we can quickly recall the RSA function, which we discussed in the previous segment. If you have not watched, please watch that. It's nothing but m power e mod n. This is the plain raw RSA function. As I said earlier, in practice, we will use padding before calling this function. The message m must be padded with some random data, otherwise this is going to be easy to break. So this is the RSA function. The question is how many m's exist so that RSA of em is same as m, okay, which means RSA is not encrypting our message. That's basically the point. We wanted to have only a few that will not be encrypted, okay, but I wanted to derive a mathematical expression for this. All right, so what I'm going to do is I'm going to solve this problem in multiple steps. I'm going to make use of homomorphic properties between mod n and p into q, okay. Remember, n is made of 2 primes p into q. So we know that Zn is isomorphic to Zp Zq pair, okay. So I may write it pair or I may show it as multiplication like this. So what it means is that any element that you are taking from mod n, right? Suppose you are working here on this clock from 0 through n minus 1. This is your n actually. This is n minus 1. This is your 1, 2, and so on. Any element you take, suppose you take an element over here, some element that gets mapped into 2 points, okay, on one clock from 0 through p minus 1. This is your p minus 1. And then you have another clock 0 through p q minus 1. So basically that's one visual representation of this mapping, okay. Any point that you take here gets mapped to a point over here and a point over here, okay. So that's the reason why we say it's a pair here, okay. All right, so why am I going to or how am I going to make use of this relationship? So I'm going to solve this problem as follows. Instead of computing RSA of m in mod n, I'm going to compute in mod p first, and I wanted to show to you how many fixed points exist for mod p, and also, of course, for mod q, and then we can combine the results to find out how many exists in mod n. That's the idea. Okay, so we are going to solve a simpler problem now. Let's say we are going to compute RSA of m as follows. We compute, I'm going to put a suffix here, p, to show to you that we are going to compute in mod p. So I wanted to know how many RSA m in mod p is same as m. Okay, how do I solve this problem? I'm going to make now some assumptions. First assumption is that let's assume for a moment that GCD of m and p is 1, meaning the message is not a multiple of p. P is a prime, right? Okay, let's assume like this. Okay, with that assumption, we can easily solve this problem as follows. So our goal is to find how many m exists such that m power e mod p is same as m, right? That's our goal. Let's assume m power e mod p is m. What does it really mean? It means since m is not a multiple of p, we can write it as m into m power e minus 1 mod p, which is still m, right? I just rewrote the m power e as follows. Okay, since you see m here and an m here, okay, what it means is that this component must be 1, otherwise you will not get an m there. Okay, so how do we do this? Now we have a simple situation. You have m power e minus 1 in mod p, right, is 1. All right, this is so far good. Okay, now we are going to make use of the fact that p is prime. If p is prime, we do know that the group z star p, which means excluding the 0, is a cyclic group. Okay, So in that case, we can imagine any element in the group. I'm going to now draw a circle here to show to you that we are talking about Z star P. Okay, Z star P means you don't have a zero there. You have all the elements from 1 through P minus 1. So you start from 1, 1, 2, and you end up at P minus 1. Okay. This is a multiplicative group, and also it's a cyclic group, meaning there exists an element which generates all the elements of this group. Okay, that means M must be same as some G, generator of the cyclic group, power I. We don't know I. So, yeah, every element of the cyclic group is some power of G, right? That's what I'm going to do now. E minus 1 mod P, okay, is equal to 1. All right. So now we can solve this easily. This implies that G power P minus 1 mod P is 1 by Fermat's theorem, for example. So any multiple of P minus 1, this actually means that I times E minus 1 is actually a multiple of P minus 1. Okay, that's good enough. So now the question is, how can we find how many I exists? Okay. Remember, for every I, G power I will be unique because G is a generator. So if we can find the unique solutions to this congruence, then we are done. And we just did linear congruence, and I have shown to you that a linear congruence, let me write it here in general as a remark. Suppose somebody gives you a linear congruence, A times X is equal to C times C mod M. You know the solution exists only if GCD of A and M divides C. Okay, the solution only exists if the GCD of A and M, right, divides your M. Okay, divides your C. Sorry. What is C in this case? C is 0. So all numbers divide 0. Okay, that's well-known fact. So that means this equation must have a solution. And we also learned that the number of solution for such a congruence is D. D is nothing but GCD of A and M. So what is A? A in this case is E minus 1, and M in this case is P minus 1. So the number of solutions for this equation, the unknown here is I, right? We know E minus 1 easily. And we also know P minus 1. Although P is private in RSA, for this calculation, we are going to compute how many points are fixed points, right? That's the reason why I say we know P minus 1. So the unknown is I, which is same as X on this equation. So anyway, the number of solutions is a GCD of E minus 1 comma P minus 1. Okay, that's basically the number of solutions to this equation, the equation in box. M power E mod P is equal to M. How many M's can we expect? We can expect GCD of P minus 1, E minus 1, P minus 1 solutions for this particular equation to have a fixed point. Okay, so all I did is actually converted this problem. The big problem we wanted to solve is M power E mod N. We converted the problem into two subproblems. One is to find M power E mod P. We learned that there are a GCD of E minus 1, P minus 1 solutions. Instead of P, we replace it by Q. We will get GCD of E minus 1, Q minus 1 solutions. And now we can combine all of these using the Chinese remainder theorem, which we talked about. All right, let's do that. So let's take a prime 11 or 7, doesn't matter. Okay, we don't need N in this case. We don't need pi, we don't need D. We can remove all of these. I just wanted to show to you how many fixed points exist. N is same as P. Okay, right. So we don't need Q. We can get rid of. All right. So remember, N is same as P. That's what I did for this demo. All right. So let's see the number of fixed points. We get 6 fixed points. What did our model say on the whiteboard? Our model said GCD of E minus 1 comma P minus 1. Okay, that many fixed points we can expect in mod P, and we can check it. What is p minus 1 in our case? P is 7, p minus 1 is 6, e is also 7. So GCD of 6 and 6 is 6. Okay, for this particular demo. That's the reason why we are seeing 6 fixed points. So we are able to predict clearly how many fixed points are there in mod P. Similarly, we can do the proof or rather a demo for a Q being 11, which is not that difficult to do. So I will not do it, but you get the point. Okay, so let's quickly fix this, and then we can move on to the. So let's see whether we can change this to 11, right? And I'll keep this NSP. I mean, logically speaking, I'm trying Q. Anyway, that doesn't matter. You should be seeing now GCD of 10,6, which is 2. So only 2 fixed points. Yep, you see the fixed points are number 1 and 10. All right, so far, so good. So what it means is that we are able to easily calculate the fixed points for mod P and mod Q. And we learned how many fixed points are there. So, okay, so what is the next step we need to do? We need to combine the fixed points of P and the fixed points of Q to obtain the fixed points of mod N, okay? Which we can easily do it as follows. So let me get back to the whiteboard. So far we have done fixed points of mod P and mod Q. We made an assumption that GCD of M comma P is 1 and GCD of M comma Q is also 1. I'm going to make use of the Chinese remainder theorem and combine the number of solutions. Okay, call this constant as R, okay, with the mod P, and another constant S. So I'm going to say another constant S is nothing but GCD of E minus 1, Q minus 1. Okay, so we learned how to compute the fixed points in mod P and mod Q, and how many rather. So R and S are known. Now we go back to the assumption we made. We made an assumption that GCD of M and P is 1, meaning M is not a multiple of P. So what happens if M is a multiple of P? If M is a multiple of P, when we do when we take an M, which is say a multiple of P, meaning M is congruent to 0 mod P, right? That's the meaning of multiple of P. When we apply Chinese remainder theorem pair or homomorphic property first, whenever M is a multiple of P, the first component will be 0. So okay, the ZP component will be 0, and the ZQ component can be something we don't know. But anyway, all of the pairs will have 0 and some number. Okay, we don't know how many numbers, but we just learned that there are yes such numbers. Okay, that will map the fixed points in mod Q. So there must be yes pairs, okay, which start with 0 something. We don't know what it is. We don't care. We get yes such pairs. Okay, and let's do the same for M being 0 mod Q. Okay, so how many pairs we'll have now? Okay, we have whenever M is a multiple of Q, the second component will be 0. So we don't care about the first component. So this is 0. The second, another pair will be something like this. So we have how many pairs now? And so on. We learned that there will be or such pairs, right? Because or such pairs have this property that we just talked about. So if I count this set, okay, this set cardinality will be yes. Okay. We do know, okay, there are yes fixed points for mod Q and or fixed points for mod P. So I'm correct. Now we can compute the overall fixed points for mod N as follows. It must be all of the elements of this set, which is made of S elements, and then R elements, right? And R times S. This is the model that tells us how many fixed points we can expect in an RSA function like this. Okay. As you can see, the most important thing is that in order for this number to be small, we would usually like this multiplication product to be small, which means we want the GCD of E minus 1, Q minus 1 to be small. Similarly, E minus 1, P minus 1 to be small. If E minus 1 and P minus 1 have a large component that is shared, then we will see a lot of fixed points. That's why in practice, the value E is one of the reasons, I must say, is a very small number. Therefore, it doesn't have many common factors with P minus 1 and Q minus 1. Okay. All right. That's basically it. We have a nice model that tells us how many fixed points are there for a given RSA function. We have S plus R times S. Okay. And we can now go and check that this is true or not. Okay. Let's do a quick check. So, okay. We are counting how many fixed points in mod n and compare against this model that we have learned. Yeah. So what we have confirmed is that there are only R plus S plus R times S fixed points. Okay. We can print count. Okay. 20 fixed points. But let me take something different. Let me try with the E to be 3. I don't know whether this will work. Let's try. Yeah, you see, when E is 3, there are only 8 fixed points. The reason being that when we did E to be 7, GCD of E minus 1, P minus 1 was a very big number. So it was, well, very big in the sense it was 6 because they both are same. But as soon as I reduce E to be 3, these two numbers have not many factors. Therefore, the number of fixed points is dropped significantly from 20 to 8. So the choice of the public exponent E matters. We don't want E to be having a lot of prime factors with P minus 1. Okay, that is the main point I would like to get across. All right. So let us summarize all the points that we discussed. So all we did is actually transform this problem of computing the fixed points in mod n to mod p and mod q. Okay. So first we assumed that m and p are relatively prime. Therefore, I can rewrite this as m into m e power e minus 1 mod p is m. And then I converted this into a linear congruence relation. And I was able to find out that the linear congruence will have R solutions for mod p and S solutions for mod q. Okay, that means there will be GCD of E minus 1, P minus 1 times we'll have fixed point in mod p, and E minus 1, Q minus 1 GCD for yes. Actually, we can also confirm that in the demo. Let's go back here. Let us just do mod p, right? And we would like to confirm that the count is nothing but R, right? That's what I said on the whiteboard, okay? Because I'm doing now mod p. Let's see whether this is true. Yeah, that's good, because we had an assertion which is satisfied 2 times. Very nice. And I'm going to increase the E to be 7. Yeah, 6, nice, because GCD of 6 and 6 is 6, and we get 6 fixed points. That's good. Let's do the same for Q. Assertion is still true. So we are correct. We checked even programmatically that our model is correct. And then we also relaxed the assumption that the M and P are relatively prime. We consider this case that M is a multiple of P. We can easily solve a solution. How many solutions are there for that equation? And then we did the same for M multiple of Q. Okay, so we have the second component is all 0 because it's multiple of q, only the first component will be different. Okay, and that is another thing that we talked about. The first component will all be different, but it will still be fixed point because we are talking about fixed points, and there are such fixed points for mod p. This point is the most important one. I have to add s and r, otherwise I'm only computing z star n, which is multiplicative group. Okay, but the question is from zn to zp zq, fixed points. Okay, so that's basically it. There are fixed points, but in real life usage, if you don't change the value of e, which is 65,537, you will not have many fixed points. There are only a few fixed points which satisfies. Well, there are only a few fixed points that will not be encrypted. Okay, that's basically my main message.